All right, so the idea with this video is for most people, the big challenge with U substitution is just determining what U should be equal to. And it's not easy, right? I wish I could tell you that, oh, it's always just going to be this and then you do this, but it's not. Like I mentioned in the previous video, it's more of a puzzle than anything else. You have to look at this and kind of play around with it and try different things. And often you try the wrong thing and you won't know it's wrong until you try to work the problem through and you get stuck. So I think the best solution is just repetition, right? Just to show a lot of different examples and talk about what U should be in each of these examples. And I think if you can get to the point where you can properly recognize what U should be equal to, the rest of this isn't that bad. So it's going to end up being the case that our U will be x squared plus 1. And how do I know that? Well, I know that because I've done this problem so many times, or these types of problems so many times. You get to the point where you can just sort of recognize them. But how would the student know that? Well, like I mentioned in the previous video, it's really just a puzzle, right? You don't know it, it's not obvious, but if you kind of think what would happen if you let your U be equal to x squared plus 1. Well, if U is x squared plus 1, then I'll have left the square root of U, which I want to point out is a really good thing because the square root of U, that's just U to the 1/2 power. And you could take the antiderivative of a variable like U raised up to a power like 1/2, no problem. And you're like, yeah, but what about this x out here? Well, look, if U is something to the second power, like x squared, then my du will involve this x. So the x and the dx will both get kind of sucked up into the du part. Can't see that? Well, let's go through the steps. If U is x squared plus 1, then du is equal to 2x dx. How do I know that? Because du over dx is 2x. The derivative of this is 2x. But remember, we don't want du over dx. We want to multiply both sides by dx to get to this form. You're like, but you don't have a 2x dx, right? But I can multiply both sides by 1/2 or divide by 2 if that's easier to see, to get that half of du is x dx. And now the pieces are going to work out really nicely, right? The x and the dx will just be a constant. And constants are really easy to deal with, and my du. And then the x squared plus 1 that's underneath the radical will all just change into the u. What I'm saying is when you do all your substitutions, this thing in red, which is really complex, turns into this thing in blue, which is really easy to evaluate, right? Maybe if you can't say that this is really easy to evaluate, let me take it one step further. The half is a constant. We can pull it out in front of the integral sign. And u to the square root of u is just u to the 1/2 power. So I just need to use the power rule to figure out this antiderivative. We're not done, to be clear. We still need to figure out the antiderivative. We still need to change the u's back into x's. There's still work to be done, but the purpose of this video is just to get comfortable with the u's. So I want you to be able to see that u has to be x squared plus 1. And you're probably at the point where you're like, okay, if you tell me what u is, I can understand how it works, but I don't feel comfortable that I could have gotten this u on my own. Well, here's another argument. What else could u be? Like, well, why don't you make u equal x? You never just want to make your u equal to x, because then your du is just dx, and you end up writing the exact same problem, except this is a u, this is u squared plus 1, and this is du. If your u is just x, it doesn't help at all. So you'll never do a substitution where u equals x, or you'll be wasting your time. You're like, well, what about if u were x squared? That's a really good question, because there's no reason why u couldn't be x squared unless you've done this problem enough and know that it just doesn't work out. Look what happens if u is x squared. If u is x squared, I'd have the square root of u plus 1, and then my du would still be 2x dx. Right? If u were x squared, my du is the exact same. So I can do the same trick to get rid of this x out here and change this into a du. The only thing that would change if I let u be equal to x squared instead of x squared plus 1 is over here I would have the square root of u plus 1. Because if the u is just the x squared, I still have this plus 1. There's a problem with the square root of u plus 1. You don't know the antiderivative of it. Or at least you're not supposed to know the antiderivative of it at this point in the class. Turns out it can be done. You can do it with the second substitution, or you can just kind of think your way through it. But the point is just my variable to the 1/2 power, the power rule definitely applies. But if it's u plus 1 in parentheses to the 1/2 power, then I'm not quite sure how to use my power rule. Or if you are, good for you, you're ahead of us, you're ahead of where we should be in this class. You're not supposed to be at the point where you're comfortable doing that. So that's why I made the u the x squared plus 1. I was thinking ahead to what I want to take the antiderivative of. So it's tricky. You're thinking about, you have all these different processes going on at the same time in your head. What could u possibly be by looking at the problem? Make sure that that'll make the du work out. So you have to immediately think about what the derivative of this is. And then think about, when I do all those changes, will that leave me with something that I could take the antiderivative of? Because if it doesn't, there's no purpose in doing the substitution in the first place. The whole point of this U-substitution is to change it into something you take the antiderivative of. If you're not getting there, you're not getting anywhere useful. I'm going to fight the urge to talk more about this and just move on. I want to show you lots of examples. I don't want to spend forever on one. This one, there's not that many options for what u could be equal to. So I guess by process of elimination, it's not too bad. It'll turn out that u is just 3x in this case. Why? Well, because if my 3x up here, this exponent were just my variable, if this were e to the u power, the antiderivative is super easy, right? That'll work. And you're like, ooh, but what about the du? Will that all work out nicely? Yeah, it'll work out super nicely. The du will just be equal to 3 dx. The 3 is just a constant. I never have any trouble with constants. Like, I don't see a 3 out here. No big deal. The 1/3, multiply both sides by a third, and you get 1/3 du is equal to dx. And now I can do all my substitutions. Substitute in, you have e not to the 3x power, because the 3x is what you're calling u. But then you're not done. You still have to change your dx into 1/3 du. You could put the third inside the integral, but as you saw in this previous problem, these constants inside the integral can be pulled out in front. So often people will skip that step and jump straight to here and recognize that, well, this is super easy. This is my favorite antiderivative in the world. I can take the antiderivative of e raised up to a power, no problem. Problem 3. Problem 3 is kind of like problem 2. It's just the harder version of problem 2. So the idea with this one is it's harder to recognize that you can change this into something that you know the antiderivative of. And if you don't see it, that's totally fine. There's not that many things that you know the antiderivative of, and once I show you, you're like, oh man, I always forget that one. Inverse trig, right? If this were 1 divided by 1 plus a variable squared, I'd be able to use inverse trig functions to figure it out. What I'm saying is if I let u equal x over 2, I'll be in good shape. And you're like, why not x over 2 squared? I'll show you why it can't be x over 2 squared in just a minute. But before I show you what it can't be, let me show you what it is. If u equals x over 2, you're like, ooh, du is really hard to figure out because I need to use the quotient rule. No, you don't. Because x over 2 is just the same as 1/2 times x. So the derivative of 1/2 times x, the x goes away and I'm left with just the 1/2. What I'm saying is du is equal to 1/2 dx. And as is often the case, I don't have a 1/2 dx in the problem. I can multiply both sides by 2 and say that 2 du is equal to dx. And now I'll be able to get rid of this dx by changing it into 2 du. Where do all the pieces go? Well, let's see. Instead of the dx, I'll write du. Instead of the constant 2 being times that thing, I'll pull the constant out in front of the integral. So I'll get the 2 there. And then I still have this one. And I'm still divided by 1 plus something squared. But instead of the x over 2, I'm going to write the letter u. I get here. And maybe you can recognize this as the derivative of arctangent of u. But again, that's an issue for the next video. The purpose of this video is just the u's and the du's, just the substitution. All right, for number 4 here, something I want you to notice is that up in the numerator here, we have this x squared. And the 2 in the x squared, the power, is 1 less than the 3 that you see in the power here. And often when you have the variable raised up to 1 less than the power to which the variable is raised up to somewhere else in the problem, that smaller of the 2 will end up being part of your du. And that kind of makes sense because the power rule is going to tell me to take 1 away from the exponent when I calculate the derivative. So if I let my u have something to do with this x cubed down here, then my du will be somewhat related to this x squared. Let me try to make that a little bit more formal. What you'll want to do for this problem is let u be equal to x cubed plus 1. And it's tempting to make u equal x cubed, and actually that'll work in this specific case, but I want to caution you against doing that, and I'll explain why in just a second. If u is x cubed plus 1, then maybe you can figure out that your du would be 3x squared dx, because du over dx is 3x squared. The derivative of the 1 just goes away, and the derivative of x cubed is the 3x squared. And yeah, you don't have a 3x squared in the problem, but you do have an x squared in the problem. So what I can do is divide both sides by 3 to get a third. Du is equal to x squared dx. Here's my x squared. Here's my dx. The 1/3 can just go out in front of the integral. And then the x cubed plus 1 down on the bottom here will just turn into a u. So when I substitute in all those different pieces, there's the 1/3. There's the antiderivative, the 1 over u, and my du. And it might not be obvious that you know the antiderivative of this guy, but think natural log. The derivative of the natural log of u is 1 over u, so the antiderivative of 1 over u is the natural log of u, except we want to put absolute value symbols around the u to make the domains match up from the different functions. Quick comment here. If we let u be equal to x cubed, the du would still be the exact same, so I'd still get the 1/3 and the du here. The only difference is now this plus 1 wouldn't go away as part of my u substitution if u were just x cubed. So what I would have would be 1 over u plus 1. And kind of like we saw up here, u plus 1 to the 1/2 power is more challenging than u to the 1/2 power. 1 over u plus 1 is more challenging than 1 over u. It turns out that you can figure out what the antiderivative of 1 over u plus 1 is equal to, but it's a better idea to change this into the antiderivative of 1 over u, as I'll be able to illustrate with more complicated examples. So maybe for now, even though it's not entirely true, pretend that if it were 1 over u plus 1, you'd be stuck and couldn't figure out the antiderivative. That's a little bit of a lie there. So therefore, you want to make it 1 over u. So therefore, you want your u to include this plus 1 and make it x cubed plus 1. This is a classic Calc 2 U-Substitution problem. You see it all the time. Often the way it's asked is instead of figuring out the integral of sine of x over cosine of x, you're asked to figure out the integral of tangent of x. And the student has to be like, oh, tangent, that's just sine over cosine, and rewrite it this way. And why would you want to rewrite it this way? Well, so that you can do a U-substitution. And you're like, oh, okay, this will be really easy. Like, I could make my u the sine, and then the du would be the cosine. And that's tempting, but that won't work. And the reason that won't work is, informally speaking, you don't want your du down in the denominator, right? Think about this dx as being times this entire thing. It's not divided by dx. The dx is not down on the bottom. The dx is up on the top, informally speaking. So in order to make sure that my du ends up on the top here, I need to make this sine the du part. So therefore my u will have to be the cosine part. So I'm going to let u equal cosine of x. And then my du, see, the derivative of cosine is negative sine of x dx. And you're like, ooh, that's a problem. I don't have a negative sine of x dx. I have a sine of x dx, right? But I could multiply both sides by -1 to get negative du, or -1 du if you prefer, is sine of x dx. And how this will work when I substitute in all the pieces is the -1 here that's attached to my du, which will be left over when I get rid of this sine of x and this dx, will go out in front of the integral because it's just a constant. It's a -1. And then I'll have 1 over u du. Make sure all the pieces check out, right? The du was the sine of x and the dx. So there's a sine of x and a dx here. Think about the sine of x up top. Oh, there it is. And then the cosine of x is the u. It's down on the bottom. Corresponds with this u right here. Finally, the sixth one here. If you stare at this guy, it turns out you could do it without U-substitutions, but you'd have to expand out this polynomial, e to the x power plus 1 to the 10th power. And that's really hard to do. That's like FOIL and then FOIL and FOIL and FOIL and do it like 10 different times. And then do all that and then distribute the e to the x through, and you'll get a really long polynomial looking thing, except the variable is e to the x. And that might be something you take the antiderivative of, but that's definitely not something you want to do. What you instead want to do is that because the derivative of e to the x is just e to the x, having e to the x show up twice here will be really useful. And you're like, wait, so I'm just going to make my u e to the x and then my du will also be e to the x? Not quite. You don't want your u to be equal to e to the x because then you'll have u plus 1 to the 10th power, and that's problematic. Kind of the same issue that we saw here with the plus 1 and we saw up here with the plus 1. We see down here with the plus 1. Instead of letting your u be equal to e to the x, if you let your u be equal to e to the x power plus 1, well, then your du works out really nice. That's just e to the x dx, right? Because du over dx equals e to the x, because the derivative of this is just e to the x, because the derivative of e to the x is e to the x, and the derivative of plus 1 is just 0. And this e to the x dx will take care of this one, and this u will take care of what's inside the parentheses here. And when all the dust settles, this will work out incredibly nicely. I'll just get the integral of u to the 10th power du. I think I want to call that good for this video. The purpose of this video was really just to try to make arguments for why the U-substitutions were what they were. I think that if you can get to the steps that you see over in blue, you'd be able to finish the problems. And maybe it's a good exercise to go through and see if you can finish them all. What I did is I wrote the answers down here below, and I tried to even show a little bit of work for how I got to that final answer for each of these different problems. So it might be worth your time going through and making sure you can solve all these. One other comment that I want to make is I always mention how you can check these and then I never do. I think checking your answers in this section can be kind of enlightening. Like for this one, for example, if we took the derivative of this final answer, the 3/2 and the 1/3, like bring power rule, 3/2 comes down in front, 3/2 times a third is just 1/2. So you have this extra constant of a half hanging out in front. You're like, ooh, that's going to be weird. But then this is raised to the 1/2 power. So we got the square root of the x squared plus 1, and you still have this 1/2 power. But then you're not done. You have to take the derivative of the x squared plus 1, which is the 2x. There's the 1/2 and the 2. Those are going to cancel each other out, and I'll be left with just an x. You can kind of see where the x, the square root of the x squared plus 1, where all the pieces kind of come from. I think that it adds to your knowledge of doing U-substitutions to check U-substitution problems by using the chain rule. Doing that not as much just to check that your answers are right, more so to sort of understand the process, to start to see where the different pieces go. It might give you some extra insight into this, which will be useful when you're trying to determine what the U's are in the first place.